All right, the next topic, energy. We will start with gravitational potential and kinetic energies. Gravitational potential energy, you should know this equation. Gravitational potential energy is equal to mgh, where m is the mass of the object, g is the gravitational field strength, also called the acceleration of free fall, and h is the vertical height. It's very important that you understand this. This height is not a slanted height, it is always a vertical height. Okay, and what is gravitational potential energy? That is the energy an object has by virtue of its position in a gravitational field. So if you consider an object on the surface of the earth, the further and further you take the object away from the earth, the greater and greater will be the height, and therefore the greater will be the gravitational potential energy. Okay, assuming that the gravitational field strength remains constant. So if we take it to great heights, then the gravitational potential, the gravitational field strength, or g, acceleration of free fall, will decrease. But here we are considering small heights. Okay, not very much further from, because if you go out of the Earth's gravitational field, then g will be 0. Okay, so we are not considering very large heights, but we are considering heights close to the surface of the Earth, so that there isn't a huge decrease in g for the increase in height that we take. So we assume g is constant, and then when we increase the height, the gravitational potential energy increases. Again, this is very important that you understand this height is the vertical height. Okay, it's the energy an object has by virtue of its gravitational field. Then we have kinetic energy. Kinetic energy is the energy an object has by virtue of its movement. Kinetic energy is also called movement energy. The faster an object is moving, the greater the kinetic energies of that object. If the object is stationary, the kinetic energy is 0, because V is 0. Then under kinetic energy, it's very important that you remember this equation. Kinetic energy, K for kinetic, E for energy. Like you see here, P for potential, E for energy. So EK means kinetic energy is equal to half mv squared, where m is the mass, v is the speed of the object. Certain students forget to square this. Remember, it's mv squared, and once you apply the equation, remember to square the velocity or square the speed. And since both are energies, the unit will be in joules. If you substitute everything here into this equation in SI units, you will get the energy also in SI units, which is joule. Okay, so here are some questions, very, very simple. Keep in mind the height is the vertical height here, and the kinetic energy increases with increasing velocity. If the velocity is 0, the kinetic energy is 0. Kinetic energy is also called movement energy. Okay, let's go through this example quickly. A brick of mass 2.2 kilograms is lifted vertically through a height of 1.24 meters. So the mass is 2.2 kilograms, g is 9.81, and the height is 1.24. The GP again is calculated as follows. GP stands for gravitational potential energy. So substituting the equation, you get the answer. Okay, very simple. Then kinetic energy. Let's go through this example. A large jumbo jet plane might have a cruising speed of 900 kilometers per hour and a flight mass of 400 tons. What would its kinetic energy be? 400 tons means 1 ton is 1000 kilograms. So you have to multiply this by 1000. So it will be 400,000 kilograms. Now we can again use this equation, half mv squared. Half mass is 400,000, or 4 into 10 to the power 5 kilograms. V, or the speed, is given, that is 900 kilometers per hour. We have to convert this to meters per second, because we want our answer in the SI unit, in joules. If you substitute in other units which are not SI units, you won't get the final answer in SI units. That's why we convert all the quantities here into SI units, so that we get our final answer also in SI units. Okay, so half mv squared, m is the mass, and then we have to get it in meters per second. So what we do is we convert this to meters per second by understanding how many kilometers, or how many meters are in a kilometer and how many seconds are in an hour. So we have 900 kilometers per hour. Now 900 kilometers is in the numerator. Okay, let's do this conversion. It's a very simple conversion, but we'll quickly go through it. Okay, if you understand the way to do this conversion, it's very simple. Okay, to do the other conversions also. So we have 900 kilometers per hour. Okay, so for 1 hour it travels 900 kilometers. So what we can do is, this kilo is a metric prefix. Kilo has a numerical value of 1000. So the sign between these two, this number and this letter, and between these two letters is a multiplication sign. So you can also write it like this, and then per hour, 900 kilometers per hour. Now we know the numerical value of k, which is 1000. So we have write 900 into 1000. Okay, 1000, sorry, into m, divided by, now 1 hour is how many? 3600 seconds. Again, if you're not sure, you can convert from hours to minutes and then minutes to seconds. Okay, if you want, we can do it that way also. Okay, we'll try that way. So we have here 1 hour times, what we can do is 60 minutes in 1 hour. So we write 60 minutes in 1 hour. So then hours and hours cancel. You see, the way I wrote the relationship is such that the units cancel out. Okay, then we have 60 seconds in 1 minute. 60 seconds in 1 minute. And then minutes and minutes cancel out. Do you see that, how I wrote this? I wrote it, the relationship, in a way so that the units cancel out. Now the unit that is in the numerator is seconds. Can you see all the other units cancel out? Unit will be seconds. So this will be, and in the denominator it's seconds, in the numerator it is meters. So 900 times 1000 is 900,000. 900,000 meters in the numerator, and 60 into 60, or okay, we can write 60 into 60 seconds in the denominator. So what happens is this 0, 0, 0, that those zeros cancel out, and then this is also, we can write this as 3 into 2. Okay, so if you want 6 into 6, 36 also we can write. Then 9 into 4 is 36. So it will be 900, or rather 9,000. So we have 3 zeros here. 9,000 divided by 36. So we can also write this as 9 into 1000. Then this, okay, I'll do that. So here numerator in meters, this is in seconds. So 9 into 1000, again, this is how you can easily do it without using a calculator. So simplify as much as possible, then you must find there is a possibility to do it without the calculator. 9 into 1, 9 into 4. Okay, so 1000 divided by 4 is 250. 250 meters per second. And once you get the answer, check whether your answer is sensible. Okay, so 250 meters per second. Now, since it's an aeroplane, yes, it can travel at this speed in 1 second, 250 meters. Okay, now this is how you convert. After that, substitute this for V in the equation, and you will get the answer in joules. And you can see this is the answer. It's 10 to the power 10. And if you want, you can convert it to megajoules or gigajoules and write it. So if you convert to gigajoules, giga is 1 billion. Okay, giga is 10 to the power of 9. So you can also write it like that. Okay, 12.5 billion joules or 12.5 gigajoules. Okay, and conversion between kinetic and potential energy. So if you consider a projectile, when a projectile is thrown up, what happens is the energy converts from kinetic to potential, and then that is when it goes up, and when it falls back down, it converts from potential to kinetic, gravitational potential energy to kinetic energy. Okay, let's consider this. We'll assume the projectile is thrown vertically upwards like that. Then this is the highest point, and then it falls back down. Okay, so when it goes up, what happens is, now initially when it is thrown, let's say it's thrown from this reference level where the height is 0. So we take the height from here. Imagine it's the ground level. Okay, so here this height is 0 here. Then let's say since the height is 0, the gravitational potential energy at this level is 0. Then what happens is thrown up when, then at the highest point it comes to a rest. So since it is thrown vertically, we know at the highest point the vertical velocity is 0. Vy is 0. Okay, so if since it is thrown vertically, we assume there is no horizontal motion. Okay, so it goes vertically up and falls vertically down. So at this highest point, since it comes to a momentary stop, the kinetic energy is 0.
Yes.
Okay, so here it is at the maximum height also. So it has maximum GPE. Maximum. Okay, but over here when it was thrown, the kinetic energy was maximum, because as soon as it is thrown, it has its maximum velocity. Then what happens? The velocity decrease becomes 0. So here the kinetic energy is maximum. Okay, over here the kinetic energy is maximum, then the speed decrease becomes 0, and then the potential energy is here maximum. Then what happens is it falls back down. Okay, so it falls. Then when it falls, what happens is the speed starts increasing, the height starts decreasing. So when the height is decreasing, GPE equals mgh. When the height decreases, the gravitational potential energy decreases. And also, you know, when the speed increases, kinetic energy equals half mv squared. Okay, mass is constant. So when the speed increases, what happens? The kinetic energy increases. So from here to here, what happens is the gravitational potential energy decreases and the kinetic energy increases. From here to here, the height is increasing, but the speed is decreasing. So gravitational potential energy is increasing, kinetic energy is decreasing. So what happens here is, according to the law of conservation of energy, assuming there is no air resistance here, energy cannot be created or destroyed, but it can be converted. That is the law of conservation of energy. So what happens here is, when it is going up, its speed is decreasing. That means its kinetic energy is decreasing. If its kinetic energy is decreasing, that kinetic energy should convert to some other form of energy, and that form which it converts to is gravitational potential energy. So whatever decrease in kinetic energy when it goes up is equal to an increase in gravitational potential energy. The same thing happens when it comes back down, but in the opposite way. So when it falls back down, the height is decreasing. Okay, the height is decreasing. The height is decreasing. All right. So if height is decreasing, what happens is the gravitational potential energy is decreasing. When the gravitational potential energy decreases, the kinetic energy increases, because whatever decrease in gravitational potential energy should be equal to an increase in kinetic energy, because the energy is not converting to any other forms. Okay, and according to the law of conservation of energy, energy cannot be created or destroyed. It can only be converted from one form to another form. Okay, so that's what they are doing here. They are using that equation, kinetic energy equals gravitational potential energy.
So I have small past paper questions, sir.
Yeah.
So
Shall we finish this off? I think you will be able to do it by yourself afterwards, once we finish this chapter. Okay, so what we can do is, for the upward motion, we can write the gravitational potential energy is what? mgh. So it goes to this height. Let's call this height h. Okay, so mgh is equal to half mv squared. Okay, so mgh is the gravitational potential energy. So whatever kinetic energy was here totally converts to gravitational potential energy here, because there is no friction or any other forms of energy that it converts to. We assume that. Okay, so whatever kinetic energy here is equal to the gravitational potential energy here, and whatever gravitational potential energy here, all of it converts to kinetic energy here. Okay, because it has its maximum kinetic energy. So here and here the speeds are the same, but the velocities are opposite in direction. So that's how they write this equation. Now you can see the masses cancel out, and then if you rearrange this equation, you can get v. You can get the speed here at this point, or also you can say you can get the speed with which it was thrown from this level. So that's what they are doing here. mgh equals half mv squared, and then they make v the subject of the equation. Okay, they make v the subject of the equation, and then we get this. Okay. Also, you can make h the subject of the equation. If you make h the subject of the equation, we will get this. All right. Any questions?
No, sir.
Okay, so here is an example where you have to use that now. Here what is happening is something is dropped. How fast would a penny hit the ground if it were dropped from the top of Nelson's column, which is 52 meters tall? So from here to here it is dropped. So here it has its maximum gravitational potential energy, and over here it will have its maximum kinetic energy, because all the gravitational potential energy here converts to kinetic energy here, assuming there is no friction or other frictional forces which will convert to energy to any other forms. So then we can use this equation which we got from here by setting the kinetic energy equal to gravitational potential energy. Then we get this. Okay, and we know the height. They tell us that is 52 meters. So we substitute that g is 9.10. Using this vertical downwards, we get 31.9. Okay. How, next example, how high would water from a fountain rise if it were ejected vertically upwards from a spout 13.5 meters per second? Okay, so they have given us the height. We are supposed to find, sorry, they have given us the initial speed. We are supposed to find the height. Again, we can use this equation, but since we are supposed to find the height, so we get both of these equations by equating these two. Okay, if you equate these two and make v the subject, you will get this. If you equate these two and make h the subject, you will get this. Okay, so here if you make h the subject, you will get this, and then it's very simple from there. Directly substitute. So you know v, so substitute v there. So here what happens is, why we can equate these two, because all the gravitational potential energy converts to kinetic energy, all the kinetic energy converts to gravitational potential energy. So here what happens is, water from a fountain rise vertically upwards. So initial velocity is this much. So how high it would rise means at the highest point, all the kinetic energy at the bottom where it was having this speed converts to kinetic energy at the top. Gravitational potential energy at the top. So at the bottom it has maximum. So it's something like this. So at the bottom it has maximum kinetic energy. At the top kinetic energy is 0. Gravitational potential energy is maximum. Is that clear? Any questions?
Yes, sir.
Yeah, what do you say?
Sir, no, sir, it's clear, sir.
Okay, so you asked me about paper 3, unit 3. So here is an experiment. All right. So this is to investigate G from energy conservation. Okay, again you can see here what happens is, all the potential energy converts to kinetic energy. So say they set this equal and make v square the subject of the equation, you get this, and then make G the subject of the equation, and using this you can find the gravitational field strength. So they have an instrument to measure maybe the velocity. Yeah, see, measure the velocity. So they change the height and they measure the velocity, and they probably plot a graph of v squared versus h, and then from the gradient you can find the gravitational field strength. Okay, then you can do all these questions. These definitions are very important. The next chapter is work and power. Again, very simple here. What you have to understand is, the work done is equal to the energy transformed. Okay, so very important is what work, you have to understand this. Work done, the O-level class also you would have learned this. Work done equals energy transformed. Energy transformed.
So
okay,
work done, sir, vector or a scalar?
Scalar, because anything you can remember which has the unit joule is a scalar. Okay, energy has the unit joule, work has the unit joule, so that is a scalar. Okay, so for example here you can see work done is what? Force into distance moved in the direction of the force. This is very important. Distance moved in the direction of the force is extremely important. What did you say?
So in one past paper question, they gave force into displacement. Then it's a vector, right?
No. What vector is this part actually, because it's moving in a certain direction. Force is a vector. We can consider, okay, distance moved in a certain direction. Now, if you consider this as a vector, vector times vector is not always a vector. Here it's a scalar. Vector times vector is giving a scalar. You see here? Okay. So no need to worry about that part. You remember work done is a scalar quantity. Power is a scalar. Energy is a scalar. All those are scalars. Okay. So what happens is she lifts this up 1.24 meters. So the mass of the object or the weight of the object that she lifts is the force, because she has to apply the same amount of force to lift it up. And she moves this a distance of 1.24 meters. Okay, so you can see here the mass of one brick is 2.2, and we first get the weight because the force is the weight. The same force she has to apply the other way, which is equal in magnitude to the weight. And then the distance moved in the direction of that force is 1.24. So you get this. So what happens is when she does work, this much work to increase the gravitational potential energy, of the bricks. Okay, do you understand? Because what I told you earlier was what work done is equal to energy transferred or transformed. Better word is actually transferred. Okay, energy transferred. Work done is energy transferred. So what she is doing is when she lifts this, she does work to increase the gravitational potential energy of the stones, of the bricks. You know, when the bricks are here, the gravitational potential energy is 0. But once she lifts the bricks here, then the gravitational potential energy is
increasing.
Yeah, it's increasing, and it is equal to this value. Okay, if one brick is lifted to this point, the mgh, can you understand that? Mgh, see, mgh, h is 1.24. So can you understand that the work she did is the same as the gravitational potential energy gained by the brick? The work she did in lifting a brick to a height of 1.24 meters is the same as amount of gravitational potential energy gained by a brick. Is that clear? So that illustrates this. Work done is equal to energy transform. So what work she did is equal to the energy, gravitational potential energy increase of the brick. Okay, so note that this is the same amount of energy as we calculated for the gravitational potential energy of this same brick undergoing the same lift force in section 2.2.1. Okay. Now, if the forces are acting at an angle, then you have to resolve the forces in that at that angle and then get the value. Okay. So you can see here F is equal to mg cosine theta. So we have work done is what? The force into the distance moved in the direction of the force. Okay. So we have here the force is what? Mg cosine theta. Now look at this child. So the weight is acting this way, but she is moving in this direction. So it will be W cosine theta. We have to take the component in the direction of motion. Or work done is what? Force into distance moved in the direction of the force. Okay, so we can either take it this way, or we will have to resolve or we will have to take the height in this direction. So either way we have to do it. Okay, so we can either resolve the force this way, or we can take the height this way. The weight force is this way, the distance moved in the direction of this weight force is in the vertical direction. So we can either take the vertical height and multiply it by the weight, or we can take the component of the weight in this direction and multiply it by this direction. Okay, so we have F equals mg cosine theta. That mg cosine theta is the component of the weight in this direction. Okay, that is the force in this direction. Now what happens is when the girl initially slides, what happens? Maybe she goes down, and then due to friction she may slow down. Okay, so let's say if she has the maximum velocity here, then when she comes somewhere down there, let's say she stops, So what happens is all that gravitational potential energy converted to kinetic energy and friction over here. Okay, if you draw a diagram, you can also draw a diagram and explain this. Okay, first we will go through this part. So work done is what? mg cosine theta times s delta s. Okay, so this is actually the general formula for work done. Work done is equal to force into distance moved in the direction of the force. Actually, it is the angle between, cosine of the angle between the two vectors. Okay, the weight force and the displacement vector. Okay, so let's say the weight is this way. Here they are actually getting the resultant. Okay, what you can understand is this angle is between the two vectors. Is that clear? So the displacement is this way, the weight force is this way, and the angle is between them. So the angle between the weight force vector and the displacement vector is the angle theta. Okay, so the work done is what? Fs, the force times the displacement, because it's what? Force into distance moved in the direction of the force. So the force times the displacement times cosine theta. Any questions?
No, sir.
Okay, then the next equation is, actually we can do more questions involving this. The Cambridge book has some good questions which are actually very good questions explaining this topic much better. Okay, all right, so the next topic is power. Again, you have to remember this equation for power. Power is energy over time or work over time. These two equations are important here. Energy, because work done is energy transferred. I told you earlier, work done is energy transferred or transformed. The better word is energy transferred. So some textbooks say transformed, energy converted. So best word is energy transferred. Work done is energy transferred. So since we have work done is equal to energy transferred, now can you see here, the numerator is the one that is different. The denominator is the same. Energy transferred, work done. Work done equals energy transfer. So time for the energy transfer, time for the work done, work to be done or work done. So energy over time or work over time. Then also we know work done is what? Force into distance moved in the direction of the force. So if you replace work done with F delta S here, so we take this equation, and then work done is what? Force into distance moved in the direction of the force. So we get this. Okay.
Okay, sir.
Is that clear? So for delta W, we substitute F delta S. We substitute that there. Okay. Any questions? And then when you simplify, and let's say if the object was moved vertically upwards, then we are doing work against its weight force. We are moving in the opposite direction to its weight force. So what we have is what? F is what? Mg. Okay. So we have Mg, yeah, delta S. Is that clear?
Yeah.
Okay, so wait, no. So here is example. For example, the power of a forklift truck lifting a 120 kilogram crate vertically up from 5 meters in 4 seconds would be calculated as, so it is lifting it vertically. That means it applies a force which is equal in magnitude to the weight. So that's why we use the weight here, mg, 120 times 9.81. Then delta S is 5. Okay, because it moves vertically up 5 meters. The distance moved in the direction of the force is 5 meters. Even though this is weight force, the equal force is applied in the upward direction. Then the time that it was applied for was 4 seconds. So we can use this equation for power. Power is work over time, and the numerator is the work done. So this is the work done, and divided by the time. Work done divided by time will give you the power in watts. If everything is in SI units, you will get the answer also in SI units, which is watt. So this is in watt. We can convert it to kilowatt, divide by 1000 kilowatt. And here they are explaining the metric prefixes again, what kilo, mega, giga, tera, and so on is. Okay, then these equations again are extremely important. You have to understand these equations. Again, very simple. Okay, efficiency is work done useful work done over total energy input. So output is on top, okay? Input is at the bottom in the denominator. So it's the useful work done divided by the total energy input. Sometimes we also multiply this by 100% and give it as a percentage. So if you want, you can add to this equation times 100% so that you get your answer in terms of a percentage. Same thing for this also. Again, can you see here work done is what? Energy transfer. So instead of writing work done here, we can also write energy. Okay, so useful energy output, useful work done divided by total energy input or total, yeah, again here total energy input, because here work done is energy transfer. Do you see the numerator here? Work
Yes.
done, energy transfer. That's why here it's energy output. And this is the useful amount of energy that we get. This is the total energy that is input. Okay. Then if we divide both numerator and denominator by time, work done over time is what? Power. So that's how they get power here. Or we can say energy over time is power. Again, we saw this equation in the O-level class also. You would have learned this. Power equals energy over time. You would have seen these equations in the O-level book. It was in the O-level textbook also.
Yes, sir.
Okay, so if you divide both numerator and denominator by time, energy over time is power. See, power output over power input. Total power input here, useful power output here, because you see useful only is in the numerator. Okay, let's go through this example so that you will understand it better. If the forklift truck referred to above lifted the crate when supplied with electrical energy from its battery at a rate of 3000 joules per second, what is its efficiency? Now in the previous part we found the power. This is the useful power, 1.47 kilowatt. Okay, so 1.47 or 1470 watt, and the input power is how much? The electrical energy that is supplied to the forklift, that is 3000 joules per second. 3000 joules every second. So this joules per second, this is watt. 3000 joules per second is watt. Is that clear? And
Yes,
see,
sir.
they write it as a percentage. And finally, this everything here is extremely important. The definitions, you have learned this in the O-level class also. Conservation of energy, work done, energy, power, efficiency equations. You should know all of this. Okay, so this chapter is good to know all the equations. And
Okay.
there are some questions here. Remember always that angle is between the displacement vector and the force vector. For work done, you have this equation for work done. So work done is what? Force into the displacement times the cosine of the angle between the two vectors. Also we can say work done is force into distance moved in the direction of the force. Okay, so what this W means is the work done, F is the force, delta S is the displacement, and cosine theta, this theta is the angle between the force vector and the displacement vector. So for example, if you consider here, this force is acting this way, and which way will the person move? This way. Is that clear? So
Yes,
the
sir.
displacement vector is this way. So if you draw an arrow, so you have to draw the line this, and the arrow is pointing to the right. So the angle between the force vector and the displacement vector is this one. Do you understand? Between the two arrows, the arrow is drawn this way. So between the two tails of the arrows, the angle is this. Is that clear?
Yes, sir.
So it will be 120 times 40 times cosine 30. Is that clear? The work
Yes.
done, it will be that.
Sir, still I couldn't understand that past paper question, sir.
What is the question?
So it's 2012.
Is it on that website?
Yes, sir. January 2012.
Okay. Can you send me the link so I can open it quickly?
Okay, sir.
So this is the end of the chapter then. And that's the end of energy. So do all the questions. Okay, there are some exam style questions also. Make sure you finish all of them, and that's the end of the chapter. Okay, I'll stop recording.